Then we can. All right. So what I'm going to do in these three lectures are really going through the very, very basic of posets. And so if you already know posets, it will be very, very easy for you. But hopefully, that's kind of like a nice review, and see how we can go from there. All right, so let me start with the definition. I just copied from my notes. So let's see here. Just let me know if you cannot see it. Is it good enough? Is it big enough for everyone?
Yes, it's fine.
Okay. So here you can see that poset here
Actually, if I
is,
may interrupt, on the right side, it's getting a little cut off.
yeah. So all right. So let me just move it so that like everyone can see it bigger. All right. And then I would just make it like this. Would that be good?
Good.
All right. So a poset here, what I mean here is the partially ordered set. So that's why it's called poset. So a poset has two things. One, you have to give me a set, and the other one is the order. And so the order it is actually a binary relation on P, and it satisfies three axioms. So the first one is reflexive, so meaning that x is less than or equal to x for x in P. Given x and y, if you give me two things, so basically it's saying that, oh, x is always less than or equal to itself. And anti-symmetry is just saying that if you have x less than or equal to y and y less than or equal to x, then the two things has to be equal. And transitivity, meaning that if you have three things and then you know x is less than y and y is less than c, then you know x is less than or equal to c. So we use the same idea of like if I write less than without the line here, so then that just means that it's not equal. And I can also use this notation or this notation as just like what we usually be comfortable with. So again, stop me if you have any question. So this is what we call a partial order. And if I can compare two things like this, like these two guys, when I can compare them together, I say that they are comparable. And then if you cannot compare them, then it's incomparable. So if you find that like, oh, I cannot compare the two things based on the ordering that we define, then we will say that is incomparable. So my goal in these three lectures are not giving any proofs, but I'm going to just like learn from examples. So I'm going to give you a bunch of examples. Before I move on, I also want to talk about one important partial order set is called the total order. So if x and y in P, I should say if x and y are comparable for all x, y in P, then we call this poset P a total order or totally ordered set. So sometimes I would just not write the ordering notation unless it's just something that ambiguous. Otherwise, I will just write a set. This is called total order, meaning that you can compare everything. So for example, our real number, right? So you can compare any two things by just using our normal comparison. So this is a total order. You can also do like rational number. You can have like positive integers, etc. So these are all total order set, and they are infinite. Totally order set. And then now let's look at something like finite. So for example, if I just have the set n here when I write this guy, this means 1 to up to n. And if I write 0, that's just the empty set. But usually I would not use this notation because everything is positive. Well, not everything, but if I write this, it means positive n. And here, the order that I'm going to do is just saying that like, oh, okay, well, the usual 1 to n, and then you order. So this is also a totally ordered set. So you just compare the integers 1 to n. So any two numbers, you can definitely compare them. We also have something called Boolean algebra. So this is the power set of 1 to n. And then the order here, instead of writing this, I'm going to write an inclusion. So what is this? This is the subset. This is the set of subsets. So B, where B is a subset in N. So this is a partial order. So this is called Boolean algebra. The reason that it's called Boolean algebra is because it's like related to the algebra, the Boolean algebra as an algebra before, well, like before we look at the poset structure. But anyway, so that's usually called a Boolean algebra or Boolean lattice or Boolean poset. And let's first of all just draw it out. When we look at poset, we usually will look at something called Hasse diagram, meaning that we draw out everything like a graph. So for example, if I have this guy here, then I'm going to say like, what is the Hasse diagram? It's like you draw out all the elements. So for example, here you have 1, 2, up to n. And then we know that like 2 is bigger than 1, we draw an edge. And then say, for example, there's a 3 here, then you draw an edge and so on. And then you have exactly one line here if you draw out the poset here. Now, what is the Boolean algebra that will look like? So let's look at n equals to maybe 3. So say, for example, n equals to 3, then that would be 1, 2, and 3. So 2n would be everything like the empty set, or 1, 2, 3, and then 1, 2, 1, 3, 2, 3, and 1, 2, 3, right? So these are all the 8 elements inside the power set. And then now we want to write out the relation. So what we usually do is like, we call it covering relation, meaning that like if you have like, say for example, so here we say that two things are related, but we also say X covers Y. Oh, sorry, Y covers X, sorry. Y covers X, meaning that, first of all, Y is bigger than X, and there is no, I should say cover. There's no other Z in P such that X is in between. So that just means that it's just directly bigger than X instead of you have something in the middle. So if you have something like this, then instead of just writing this, we are going to write something like X less than Y, but we have a dot here. So you're just saying that it's directly cover Y, directly cover X. So when you draw the graph out corresponding to your poset, each edge is just the covering relation. So for example, in the previous case, when I draw out this line here, it's basically like 2 is directly cover 1, and you don't draw this line. You don't need to draw 3 is bigger than 1 here, because if 3 is bigger than 2 and 2 is bigger than 1, by definition, then 3 must be bigger than 1, and therefore we don't see something like this. So that's how we draw Hasse diagram, and the term that I've been saying many times is Hasse diagram. All right. So using this, and then if we want to draw the Hasse diagram of the Boolean lattice, then what is that? Or like just the Boolean algebra, you can see that we start with like the empty set, and then you have 1, 2, and 3. And then they will be directly related to these, the empty set, because there's nothing that it would be smaller than the 1, 2, and 3. And then we have like, for example, 1, 2, 1, 3, and 2, 3, and then 1, 2, 3. And so we have something like this, and this, and this, and then because we are going to do the covering relation by looking at the inclusion here, like the order by inclusion. So 1, 2, the subset is 1 and 2, and also the empty set. And so we just need to line it up like this. And then 1, 3, you have this and this. And then 2, 3, you have this and this. All right. So that's the Hasse diagram of Boolean lattice. Sometimes some books use write B of 3 just to say that this is like the Boolean lattice. Sorry, here like that. All right, is that clear? All right, so let's look at more examples. So the other one that I want to look at is dn, and then here. So what is dn? Dn is the set of all m such that m is a divisor of n, right? So, and then we say a is less than b if and only if a divides b. Okay, so that just means that b is a multiple of a. So let's like look at the example, like say for example, if we have 90. Okay, so let's look at all the factors of 90, because if I want to do a D90, then that's all the factors of 90. Then that would be 1, 2, 3, 5, and then 10, and then 15, 18, 30, 45, and 90, I assume. You forgot 9. I didn't put 9. Okay, 9. Thank you. All right, and then now we try to write it out. So we know that like, okay, well, 1 would be the smallest one. Yes. Oh, okay. Sorry. Yes, 6 and 9. So 1 would be the smallest one. And let's see. And then we will have 2, 3, and 5, which are directly above 1, and they are just the prime factors, right? And then afterwards, then 2 and 3, you will get 6, right? And then 3 is actually going to give me something like 9, right? And then we will also have 2 square is not like we would not have 4 because there's no 4 here. So we already taken out 1, 2, 3, 5, 6, and 9, and then we have a 10. So 10 is actually covering both 2 and 5. So I have a 10 here, and also I have a 15. So let me just clear some space so that I have space for that. 10 is this one and this one, and then we have this too, so that's 15. And then now we will have 18. So that would be 6 and 9 would cover the 18, sorry, covered by 18. Right? So 18. And then we'll have 30, which would be 6 and 10 and 15. And then we also have 45, which is covering 9 and 15. And then afterwards, then we will have the 90. So let's just put the 90 here. And then we're done. right? So we put everything. So we have the 18, 30, 45, and 90. So that's the Hasse diagram. And you can see that the relation here, if you draw an edge, meaning that if you do the division, you will get a prime factor, right? So that's another example of a poset. So this is D90. All right. And what else? And then another one I want to talk about, like, so all these are like related to different areas. You can see that like this one is actually related to number theory. And I'm going to show you something more related to like combinatorics. So usually we call it pi n. And then that's less than. So what is that? So pi n here is the B such that B is a subpartition. So it's the set of all subpartitions of n. It's a set partition of the sets n. Okay. And then what does that mean by B is less than B prime? So that just means that if and only if every block of B is in some block of B prime. So, or you can say B is a refinement of B. So let me give you an example. So for example, 1, 3, 7, 2, 4, 6, 5, 8, 9 is actually less than 1, 3, 4, 6, 7, 2, 5, 8, 9. Okay, so they're blocks. So you have 4 blocks here. And then you can see that 1, 3, 7 is in this block, 4, 6 is in this block. And then you will have 2 is this block, and then this is in this block. Okay, so then you can see that this is a refinement of this one, so that is the smaller one. So they are comparable in this case, and that is called as a set partition. And some interesting fact, other than just talking about the poset itself, is that like if you look at the number of set partition of n, this guy is famous. It's called the Bell number. And then if you want to look at the OEIS and see all these different ways to describe it, is in 000110. And the Bell number is like 1, 2, 5, 15, 52, 203, etc. So lots of interesting things about the Bell number. And the Bell number of n plus 1 is actually a binomial transform. So nk of Bell number of k, where k is from 0 to n. So they satisfy some very nice relation between itself. And also if you look at the exponential generating function of Bell number of n times t to the power n over n factorial is, so n bigger than or equal to 1, and it's actually e to the power t minus 1. I may mess up with the starting thing, but like it does have like a very nice formula here. I don't remember whether I should have a 0. We have to check it again. But that's the idea. Like Bell number does have a lots of like nice relation and formulas, and it's very important in combinatorics. So it also have this refinement to make a poset, and later on you realize that that's a lattice. So now let's draw an example of it. So let's try to do n equals to 4. Okay, so let's do, if you're watching the video, I would highly recommend you to actually do it on paper by yourself. So for example, if I start with 1, 2, 3, 4, that's the most refined one. So that is the lowest one. And you can tell like the highest one would be just the block 1, 2, 3, 4. And then the next one that you will have, and you can actually count, is that there are, the next one is the next level would be like this: 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3, 2, 3, 1, 4, 2, 4. Let me just use 1, 1, 2, 4, and 3, and 1, 3, 4, 1, 2, 3, and 4. 1, 2, 3, 4. So let me just reorder this one. So then you will see that, oh, I can just do this. So that's the first layer. And then afterwards, you can just combine things. So you can think about what is this a refinement of? You can be a refinement of, say, 1, 2, 3, and 4, or 1, 2, 4, and 3, right? And or you can do 1, 2, 3, 4, right? So you can either combine this with this, or you can combine this with this, or combine this with this. And then you can do all the things like that. So you will have 1, 2, 3, 4. In this case, 1, 2, 3, 4. 1, 3, 4, and 2. So we don't have that. 1, 3, 4, and 2. And then also we can have 1, 3, and 2, 4. And you can actually count. There are 7 of them. So we already found 5 of them. The other 2 would be 1, 4, 2, 3, and also 1, 2, 3, 4. And then now you can easily just join. So for example, we already said that this one, and this one are this in a covering relation. And then this and this will be covering relation. 1, 3, 4, and 2 is a covering relation, and 1, 3, 2, 4 is a covering relation, and then and so on and so forth. And then I will let you to finish it on your own. That would be a good exercise. And then afterwards, everything is just a refinement of the previous one. Okay. So you will have something like this. Okay. And so I have 4 more that I want to introduce to you, like, because later on we are going to look at the properties of these guys. Next one that I want to talk about is the composition of n, and then with a relation. So what is a composition of n? So a composition of n is just, so composition of n is just like a sequence of positive integers such that, so these are all positive integers. And then such that when you add them up, equals to n. Okay. And if you are already in combinatorics, you may already know that we write it in this way. Okay, so this is just saying that it's a composition of n. And some people would like to say that it's a strong composition, meaning that you don't allow 0. Okay, so then how am I going to tell whether 2 compositions are related? So alpha is less than or equal to beta if and only if alpha is a refinement of beta. So what do I mean by that? So for example, if you look at 2, 3, 2, 1, 3, okay, it is a refinement of 2, 5, and 4 because like this and this are just chopping the 5 and the 4, sorry, the 5 and the 4 in a smaller pieces. But if I just swap the order and say 2, 3, 1, 2, 3, then it's just not a refinement of 2, 5, 4 because you have no way to really put the 5 together when you have 3, 1, and 2. Okay. All right. So this actually gives you another poset. And let's draw it out. Okay, so we will have the smallest one. Say, for example, we are going to look at n equals 4. The smallest one will be 1, 1, 1, 1, right? And then afterwards, like, think about how do you do, like, refinement. So this is a refinement of which one? Well, it's refinement of everyone, but like directly below, it would be 2, 1, 1, right? And then 1, 2, 1, and then 1, 1, 2. So that's a refinement. So let me just draw it here so that it's more symmetric. Oops. All right, and then afterwards you can further refine. So you can do a 3, 1, and then you can do a 2, 2, and you can do a 1, 3. I'm sorry, 2, 2, oops. 3, 1 is this guy, 2, 2 is this guy, and then 1, 3 is this guy. And then we can do a 4. All right, so that is the Hasse diagram of the composition of 4. Do you see this shape before? Right, this is exactly the same. You can see that that's the same as B3 that we just looked at. Right, at least the Hasse diagram is exactly the same, right? Like you can see that the two shapes. Let me just copy so that you can see. Oops, you can see that. So see, like these two are exactly the same thing. So then you can easily think about as like isomorphic because you can just rename your elements and then the relations are exactly the same. So now, like that's a question is like, is it always true that composition of n plus 1 is isomorphic to Bn? Right? If so, like how are you going to construct the isomorphism? And the isomorphism is not just bijection because you also have to preserve the order, right? So is it always true? So we are going to talk about it soon because I have to define what does that even mean and how to set it up. But this is something that we already observe by just looking at example. All right. So any questions so far? All right, if not, then we move on to another one, which is more in linear algebra. So we call B and Q, and then inclusion. Here, B and Q is all the subspace, the set of all subspaces of FQN. All right, and then just order by inclusion. So this actually also gives you a poset. So now let's just do an example on say for example B23. Okay. So B23 is just F3, all the subspaces of F23. So let's see. Subspaces of F23. All right, so how do we construct them? So the subspaces, let's list all the subspaces of F32. So it's like either you just have the 0-dimension one, right? Or why do I use this one? We have 0, 0, so generated by the 0, 0. Or you can also write the notation 0, 0 if you like the same. And then we have 0, 1. Okay. So this is like kind of like a line. So it's the equivalent class. So you can think about any like things that is like this is like a basis. So generated by 0, 1. And we have 1, 0. We have generated by 1, 1. And we have generated by 1, 2. Right. And then we also have generated by 1, 0 and 0, 1. And this is exactly the full space, right? So there are these 6 of them. So 1, 2, 3, 4, 5, 6. These are the 6 subspaces of F32. And then if you order them, then let's really put it like this. So we have this guy here, and then directly below it would be this and this. And then this one also, right? Like, so let's just move it like this. These guys are incomparable because like they are not multiple of each other. And then afterwards we have this guy. So if you draw it out, it would just be like this. So this is like the Hasse diagram of this poset, all right? So all these things that I just show you here, they are all finite, right? Because I can actually write them out. And there are also posets that are infinite, but I can still draw it out. Like I cannot draw this guy, right? Because like, I mean, I can draw a real line, but I cannot draw like each of the vertex. These guys, when it's countable, you can actually draw it, but these are not like fun just because they are just one line when you're a total order. So now I'm going to show you 2 of them. They are infinite, but they are also something that you can draw it out. So the first one is in a very popular topic in algebraic combinatorics. So this S here is the disjoint union of all Sn, which is the set of all permutations. And if I have 2 permutations and I say they are related, if sigma contains pi, pi contains sigma, pi, because pi is bigger, so pi contains sigma as a pattern. So this poset is called a pattern poset. So what do I mean by that? Let's draw the Hasse diagram, then everything will be very clear. So first of all, when you have like, you can see that I start with like 0 here. So that just means that I have an empty set. And then I have the permutation, which is just 1. The permutation of 1 is 1. And then afterwards, I have the permutation 1, 2. And then you can see that like 1 is just like itself. So it contains in these 2 guys. But now things gets more interesting. Is that like, okay, how about in S3? In S3, I have like 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So what does that even mean by having it as a pattern? It's just saying that if 1, 2, meaning that you have 2 elements, A and B, such that A is less than B together. So for example, you do actually have 1, 2 here. It just means that increasing, 2 numbers are increasing. So so this, you realize that like, okay, well, I do have 1, 2. Here you have 1, 3. This is a 1, 2 pattern because this one is less than this one. So that's what that means. Okay. And then here, this guy, 2, 1 is not, but 1, 3 is actually a 1, 2 pattern because this is smaller than this. So that's this. And then here, 2, 3, 1, because of the 2, 3 here, 2 is less than 3, and so on. Except for the last one, because the last one you don't have like 1 and 2, like increasing like this. So same idea, you will see that 2, 1, meaning that you have like 2 things that the previous one is bigger than the next one. So this, you have nothing like this. So this and this are incomparable, but other things are actually all have the 2, 1 pattern, right? Because the only thing that does not have a 2-1 pattern would be always increasing, right?
Why is the empty set a permutation?
Well, it's just a permutation of n. So it's just empty, nothing there. If you want, you can start your poset from the 1 as well. It's just a convention thing. And then, but you can see that you can go, right? You can just go upward. So this is definitely an infinite poset, but you can still draw it. And then other one, that's the last example that I want to show you that has some meaning. Because there are a lot. The last one is one of my favorite, is the partition. And then this one is ordered by inclusion. And partition is just a sequence of positive integers such that they are always weakly decreasing. So it's very similar to composition here. So these guys are composition but not partition. If I want to make them a partition, I have to reorder them. So for example, 3, 3, 2, 2, 1 is a partition. Okay. And this guy is not a partition, so it's not in par. Okay. So hopefully that is clear what it means by partition. And so partition usually have a Young diagram to draw it. So I will draw the Hasse diagram so you will understand. But anyway, so par is just the set of all partitions. And then they are, so lambda is less than mu, if and only if lambda is included in mu as in Young diagram. Okay, so what is the Young diagram? If you're not in combinatorics or number theory, you may not have seen it, so I'm going to draw it out. So for example, if I have like 3, 3, 1, that's a partition of 7. So that just means that like I'm using the English notation. So I'm going to draw 3 boxes on the first row, and then 3 boxes on the second row, and then 1 box in the third row. So that's 3, 3, 1 here. Does that make sense? So 3, 3, 1. Okay, so that's a Young diagram of the partition. So now if I want to draw the Hasse diagram of this guy, then I would start with the empty. So let me just move it away. And I will draw the empty partition. So that's just the empty. And then afterwards, I will have 1 box. And then for partition of 2, it's either 2 or 1, 1. And both of them, if you draw the box out, this is 2, this is 1, 1. They both include 1 box, so that's good. Now let's look at 3. 3 would be 3, 2, 1, and 1, 1, 1. So you will have something like this, 2, 1, and 1, 1, 1. So now let's think about the 3 here. The 3 is definitely including this guy, but definitely not this guy. The 2, 1 here include both of them, right? This and this, because you have this or you have this. And then for the 1, 1, 1, you have this, right?
Can we view 2, 1 and 1, 2 as the same?
1, 2 is not partition because partition has to be decreasing. But that's a good question. And then and so on. Right? So you can actually draw, so this is called a Young lattice. And we would talk about what is a lattice, but for now, like just this, if you want, you can say this is a Young poset, and we just write a Y here to denote it. So you can see that I have 2 examples here. They are both infinite poset, but you can easily build it up. Okay. Okay. If we have time later, we can talk about different posets. We can talk about Tomari poset, tubing poset, bond lattice, etc. But these are all the interesting thing for now. All right, so I did mention one thing that I did not prove. It's like, hey, we saw that these 2 guys seems to have the same Hasse diagram, so that just means that they are isomorphic because I can just rename things. So how am I going to look at this? I'm going to give you some hint. Well, the hint is probably going to prove the whole thing because the proof is not hard. But I'm not going to like write down the proof like step by step. I just show you what's going on. So let's start with the Boolean poset here. So first of all, that's one, like, it is good for us to learn some terminology. So we start with this guy. So this guy is B3. All right. And then that's something called dual. A dual is just saying that like if X, so if I have P, this is a poset, and the dual is just saying that I have the same P. Usually some people like to use P star. It's the same P. But then this guy, the new relation is just saying that, okay, X in the new relation, if and only if Y is in the old relation, they are flip. Okay, so if you look at the Hasse diagram, it's just like really flipping the whole thing. In general, if you flip the whole thing, they are not always equal, right? Like, because like you can have something like this, right? This guy, like when you flip it, it does not look always equal. It depends. Like I should not say this one, but this one. If you use this one, when you flip, you may not see like, oh, is it always equal? I don't know. Like it's just not easy to see. So how am I going to know like when you flip, you always get the same thing? Well, first of all, it's not always true. Like when you flip your Hasse diagram, it may not always give you like the same thing. And we are going to look at more example. But if it does, if you flip your Hasse diagram and you get back the same thing, it's called self-dual. So we can see that like B3 star, if you flip it, then you will have the 0 here. You have 1, 2, 3 here, right? Same thing. So I'm just drawing it like in the opposite direction. And then we'll have this guy, and this guy. Oops. So if I draw it like this, then this means 1, 2. This means 1, 3. This means 2, 3. And then we'll have 1, 2, and 3 here. Right? They're actually the same thing. Like I can draw it like a little bit lower, but they are the same graph, right? Everything the same.
If the young lattice one, a finite one would be.
Yeah, I have to be the final one because the infinite I cannot even start. Yeah. So this is self-dual, right? So you can see that they are exactly the same, right? So you can easily find a bijection that preserves the order, right? And so now, like, okay, B3 is self-dual. And then now I'm going to tell you like a map that is like, if you took my course, you already know that's like a famous map that maps a set to a composition and is a bijection. Okay, so how do you do that? So I'm going to define it. So if you have a set of numbers, so A1, A2 up to AK, and then which is a subset in N, and then you're going to have this N plus 1. So here, okay, so and then what I'm going to do is just that I'm going to create a composition by A1, and then A2 minus A1, A3 minus A2, and so on up to N plus K minus AK. So let me give you an example. For example, if I have N equals to 10, and then I have the set 3, 4, 6, 7. And then now with this map, it's very easy. You just make a composition, start with 3, and then you use 4 minus 3. So you're trying to think about how to build the next number. So that would be 1. And then 6 minus 4, that would be 2. And then 7 minus 6 would be 1. And then now you use your 11 minus 7, that would be the 4. Okay. So that guarantees that like you can go from here to here and you can easily go back, right? To go back is easy. You just start with like 3 and then 3 plus 1 and then plus 2 and then plus 1 and that's it. Like just ignore the last guy. Okay, so that's a bijection between like a set, like the power set of n and also the composition of n plus 1. All right, so so now if you use this, then you will be able to create the map that we want. Okay, so that's my hint. I highly recommend you to go and try to fill in the blanks and then try to see why they are the same. All right, so that just means that like, yeah, they are just disguised. Like the two things that I said, sorry, I'm scrolling. So this one, this is nothing new. They are actually essentially just Bn minus 1. Okay, so later on when I go to talk about different characteristics of things, then I'm going to just look at one of them, not both of them, because they are going to give you exactly the same thing. All right, so now you can see that I use isomorphism here. So I'm just going to define what is an isomorphism. So if I have P to Q is an order preserving map. What does that mean? That just means that if S is smaller than T in P, implies your image would also satisfy the same type of relation. All right. And if it is isomorphism, then that just means that you have if and only if. Okay. So like when you try to say they are really the same, then basically you're telling me that their Hasse diagram are the same because they preserve their order. All right, so now to really make things interesting afterwards, we need to set up like some more examples. These examples are great already, but I do want to show more. So I'm going to look at all the Hasse diagram because you can see that everything just based on Hasse diagram, right? So if you know the Hasse diagram, you basically know the poset. Either like, even if you have different interpretation of it, they are just isomorphic. So I'm going to look at the basic poset when you have exactly 4 things, okay? And see how, like, what they are. And again, if you have time or if you're currently at home and you have a blank paper, I would recommend you to do it by yourself and see if you get every single thing. All right, so if I have exactly one thing, then the poset has just 1 dot. You have nothing to compare. If you have 2 things, then you have 2 dots, right? But then you can either have incomparable or you can just have like a relation like this. I don't know what's going on. Let me just share again. You see my screen? Okay. And then if it says 3, then I will have 3 dots, right? Or I can compare 2 of them and then one is incomparable. Or if you like, you can do this, right? Or you can do the flip. When you flip it, you can see that they are just like the dual, right? But then they're not isomorphic. They're not the same thing because this has 1 guy bigger than both of them. This one has 1 guy, 2 guys bigger than the other one. So they are not preserving the order. Like you're not going to have like an order preserving isomorphism like that, but they are dual. Okay. And then this one, if you flip, is self-dual. This one, if you flip, is self-dual. And then the last one would be 3 things here. Okay, so that one is easy. And now let's look at p equals to 4. And we are going to like next lecture, we are going to use all of these to like think about different terminologies. But for now, I'm going to just set up all these examples. So if you have 4 dots, you can either do this. So like it's easy to create a new one by just the old one by just having 1 dot, right? Like, so I can just set this guy up here, and then I just add 1 dot to each of them. Then of course, I already get like a poset, right? So that's one way. But I can also, of course, do more. So I can have, what if I have like things like two thing, like this and this, or I can do this and this, okay? So spoiler alert, there are 16 of them. And I'm going to draw them out. So 1, 2, 3, 4, 5, 6, 7. And the other one that has 2 would be this one. Okay. And then we'll have either 1, 3. So 3 things below, or you can flip it. So they are dual of each other. You can have like this one, but then it's like this, or you can have a Y. You can have something like this, and this one is like that, or you can flip it. And then let's see, 2 more. I can have this guy, and then I can have this guy. Okay, so I drew all of this out, and I told you that that's like 16 of them, but is it actually true? Like, so for example, how about this guy? Right? Is this guy is not anywhere here. So why didn't I draw it out? Do you see where that is?
Isn't it though?
Yeah, so this is actually the same as this one. Okay, because it's because like this is bigger than 2 of them, this is bigger than the other 2 of them, and these 2 actually are incomparable, so actually it's this guy. Okay, so there are different ways to draw the same graph, but the order actually matters. So for example, this guy is not the same as this guy. It's not the same. Why is that? Because you can see that like there are 2 things that are kind of minimal, and there's only 1 thing that's minimal here, so they are not the same. So you have to be careful. It's not really similar to just graph. The order actually matter. Okay.
If you
All right.
identify all of the diagrams with their duals, is that just looking at graphs? If you say something and its dual are the same, is that just the same as looking at the graph structure?
So like if you are looking at graphs, right? Like if it's not directed graph, then they are the same thing. But actually, all the Hasse diagram are secretly a directed graph, because we can just think about all these edges are going up, right? So then if I draw it like this, then it's not the same as this guy, right? So like Hasse diagram is secretly a directed graph. All the edge actually has a direction, but because all the direction just goes up, so we're lazy and they just don't draw the arrow up. Okay, so that's the reason why you will see like these things are dual in the graph. They are the same thing, but they are actually not the same because of the direction. Does that make sense?
And 2 different directed graphs will give you 2 different posts.
Yeah. All right. So let's see. There are, so now like we just talk about something like graphs. Let's talk about something like a subgraph, but we call it subposet. Okay, so it's just like when you have graph, you can have different ways to make a subgraph. So when I'm going to talk about subposets, there are 3 different kinds of subposet. And I think after this, then it would be a good stopping point, and then I will like resume next time so that you have the terminology to understand more. So all right, so like what is so if I have like a subposet, we call it is a weak subposet of P. So first of all, subposet, of course, you have to be inside, okay? But S is less than T, less than or equal to T in Q implies S is less than or equal to T in P. Okay, so that's the weak subposet. So let me give you an example. So for example, this guy, if I have A, B, C, three things, and then just order in this way is one of the 16 of them. This guy is a weak subposet of this guy, A, B, C, and D. Okay. So you can see that this guy is a subset of this guy. Like just look at the elements, and then if you have an edge here, then you have an edge here. That's what it is. So if you don't have an edge here, then that's not a subposet. That's what it means. Okay, so that's that. Okay, so now another one is called P is a refinement. Refinement is another type of subposet. Like, well, Q would be a subposet of P if P is a refinement of Q. So what is this? This is a special type of weak subposet. It's like Q is a weak subposet of P and Q are the same set. Okay, so for example, the previous one is not a refinement because your Q and the P are not the same set. But if I just add, if I just remove, so for example, this guy, if I remove the D from here, then it is a refinement. So this guy is a refinement of this guy, right? And why is it called refinement? Because you put in more stuff. So that's what refinement. Now, the most important one, I'll leave it to the last one, is the induced subposet of P. That is the one that most of the literature, when they say subposet or sublattice, they mean this one. But it's not always, because there are different ways to create it. So you have to be quite careful. So from now on, if I just say subposet without saying anything, then I mean the induced subposet. Otherwise, I'm talking like I would tell you. Okay.
The notion of strong. If weak,
Yes, sir.
What's that? Yeah, so it's kind of like the strong.
this is the strong.
So the induced subposet here is just saying that if Q is in P, and also satisfy S is like comparable, like S is less than or equal to T in Q, if and only if S is less than or equal to P in T. Okay, so if P and Q are the same, then it has to be the same, right? This is for all ST in Q. So it's very similar to your induced graph, because it's just saying that if you take all the vertex as a subset, then your induced graph are including all the lines. So for example, like here, this guy is a weak subposet, but it is not an induced subposet, right? Because if it is induced, I have to have this guy. So to fix it, I just need to draw this line here. Then it is. Does that make sense? Okay, so that's like what that is. But it's not always just the shape. These guys, like the naming matters. So for example, like if I have A, B, C, and this guy, and then also like here, A, B, C, and D here. Okay, so now is this an induced subposet, right? Like, then that's definitely not, right? Because like the B and the C should have like a line, right? So it's not, but so not induced. But it is a subposet, like a weak one. But if I just change this as A, C, and D, and then same thing on the right-hand side here, okay, then it is. Because A, C, and D, the relation, right? Even though I don't have an actual line that links A and C, is actually there, right? So A and C are comparable with C is bigger than A, and then you have a D here, so this is induced. All right, does that make sense? So these are all like the subposet, like it is going to be crucial later on when we talk about the distributive lattice, because like you have to know, like you have to identify a sublattice inside, and what does that mean by sublattice? When I say a sublattice, they are both lattices, and also like we are talking about the induced version, not the other ones. All right, so that's why like I need to set up all the terminologies. And one more thing before I end, is that how many, like if I give you a P, then the number of induced subposet would be just 2 to the number of the size of P. Okay, so you can like think about why. All right, so I will stop here because that's kind of like an hour already. All right. So if you have any questions, just like let me know.